let's say we had a function, f of x equals x squared, which I've drawn on the grid on the right, and let's say we wanted to find the area under the curve to the x-axis. And we wanted to do this over the interval 0 to 1. One way to do this is to break the interval up into equal subintervals. So let's say we wanted to break it up into 4 equal subintervals so that we would have a quarter, a half, and 3/4. So we've broken up the interval from 0 to 1 into 4 equal subintervals. In this example, we're going to use the left-hand endpoint. So what we do is we find the left-hand endpoints on the curve for each of the intervals and then make a series of rectangles with the adjacent subintervals. So starting with our first left-hand endpoint at the left, it would be here, 0, 0. Draw a horizontal line over to the first subinterval, and in this case it's just a straight line, it's not a rectangle, but that is just the nature of where the endpoint was on our curve. And then we continue the process for the subsequent subinterval. So our left-hand endpoint at a quarter would be right here. Draw a horizontal line over to the adjacent endpoint and form a rectangle. Continuing with 1/2, our left-hand endpoint would be right there. Draw a horizontal line over to the adjacent subinterval and form a rectangle. And continuing at 3/4, left-hand endpoint would be here. Horizontal line over to the adjacent subinterval, form a rectangle. And thus our approximation of the area under the curve would represent the addition of all the areas of these rectangles. We'll call the first rectangle area A1, second rectangle's area A2, third rectangle's area A3, and A4 for the fourth rectangle's area. And so the area total would be the addition of all the areas of these rectangles. To solve this equation, we will need to know the coordinates of each of the 4 left-hand endpoints. For the fourth rectangle, the left-hand endpoint would be 3/4 for x. Substituting 3/4 into our function, we would end up with 9/16. Similarly, for the third endpoint for rectangle 3, we would have x being 1/2. Substitution into the function, we'd end up with 1/4. And for the second endpoint here, we'd have x being 1/4, and substitution into the function would be f of x would be 1/16. And finally, for the last endpoint, the far left-hand side, this would be 0 and 0. So the area of rectangle 1 would be its height times its width. Now in this case the height is 0, so it would be 0 times 1/4. The area of rectangle 2 would be its height times its width, which would be, its height would be 1/16 times 1/4. The area of rectangle 3 would be its height times its width, which would be 1/4 times 1/4. And finally, the area of the fourth rectangle would be its height times its width, or 9/16 times 1/4. And if we work this out, we would end up with 0 plus 1/64 plus 1/16 plus 9/64. To add these fractions, we need a common denominator, which is 64. So when we represent 1/16 out of 64. We multiply 16 by 4 to get 64. So we'd multiply the top by 4 as well to give us 4/64 as its equivalent fraction. And if we work this out, we would get 1 plus 4 is 5 plus 9 is 14/64, which works out to be decimal 21875 in whatever units squared that we're using. So our approximation of the area under the curve from x squared down to the x-axis over the interval 0 to 1 using the left-hand endpoints is 0.21875 units squared, which, as we can see from the graph, is an underestimate of the actual area under the curve. If we wanted to get a better approximation of the area under the curve, we would reduce the width of the rectangles. So in other words, we'd increase the number of subintervals. And the best approximation would occur when the limit of the width of the rectangles approaches 0.